Today we're going to discuss section 15.5, which involves acid-base indicators. So let's talk about finding the equivalence point. There are two ways to do this. First is to use a pH meter, so plot the titration curve, and then the center of the vertical region is your equivalence point, which remember is where your H plus is equal to your OH minus concentration. The second way is to use an acid-base indicator. This marks what's called the end point of our titration by changing color. Now, end point is not the same thing as equivalence point. Okay, end point is where the indicator will change color, indicating a change from acid to base, but it won't necessarily be the same pH point as the equivalence point. And so you have to be very careful in your selection of an indicator. Most acid-base indicators are very complex molecules that are essentially weak acids. And so it's one color when the proton is attached, and then it's a different color when the proton is absent. One example of this is phenolphthalein. It's colorless in an acid solution, but it turns pink when you get to a basic solution. In order to see a color change, you have to have 1/10 of the initial form needs to be converted to the other form before a color can be seen. Oh, and I see a spelling mistake. This should be form, not from. And so here's our equation. In minus stands for the basic form of the indicator, and HIN stands for the acidic form of the indicator. Now, usually, because we are titrating an acid, our initial form is the acidic form, and so then we have 1/10 of that being IN minus. Let's look at an example. Okay, so bromothiamyl blue, which is another indicator, has an indicator with a Ka value of 1 × 10 to the -7. It's yellow in the acidic form and blue in the basic form. Okay, let's say we put a few drops of this indicator in a strongly acidic solution. If the solution is then titrated with a strong base, at what pH will we see the color change? Okay, so let's start with our Ka value. We know that the Ka is equal to 1 × 10 to the -7, and we can write the equilibrium expression so that Ka value is equal to H plus, In minus, because that's the basic of our indicator, and HIN since that's the acidic form of our indicator. Well, since we know that we are going to see a color change, because we're trying to find the pH at which that occurs, and that color change, the ratio of the basic form of the indicator divided by the acidic form is equal to 1/10, we can substitute this into our case of A. So this equals H plus. Our basic form is 1, and our acidic form is 10. And if we solve for that, we get that our H plus is equal to 1 × 10 to the -6, which gives us a pH of 6. So at a pH of 6, we should see the color change. We can also use the EndersonHasselbalch equation to help solve these problems or determine the pH at which the indicator changes color. And so if we take our EndersonHasselbalch equation, pH equals pKa plus the log of the base over the acid, in this case we're substituting our indicator in there, we know that the ratio of In over HIN is 1/10. And so if we plug that in, we get that our pH is equal to pKa plus the log of 1/10. Well, log of 1/10 is -1, so that comes out to pKa minus 1. So for bromothiamyl blue, since our Ka was 1 × 10 to the -7, that means that the pKa is equal to 7, and then that means that if we want to plug that into our pH, pH is equal to our pKa minus 1, which is 6. And that's what we got using the other method in the example. So you have a couple different options here. So we've talked about titrating an acidic solution, but when we titrate a basic solution, that means that our initial form is the basic part of the indicator. And so now our ratio becomes 10/1. And so if we take that and substitute it into our EndersonHasselbalch, we get pH is equal to pKa plus log of 10/1. Well, log of 10/1 is 1, and so it comes out to pKa plus 1. For our acidic solution, it was pKa minus 1. So for bromothymol blue, if we were doing this with a basic solution, it would be 7, because that's our pKa, plus 1, and that would give us a pH of 8, where we would see the color change. If we did this with an acid solution, our initial is our HIN, which is yellow in color, and we know the color change would occur at a pH of 6. For our base, because we're starting with the basic part, and that's blue, we know a color change would occur at a pH of 8. So this gives us a range of pKa plus or minus 1. In this case, for bromothymol blue, it's 6 to 8. And so by knowing these ranges, it can help you choose an indicator with an endpoint, which is this, and an equivalence point as close as possible. You determine your equivalence point based on stoichiometry. You want to make sure it's within that range for your endpoint. Okay, when we titrate a strong acid and a strong base, we know that the equivalence point occurs at a pH of 7. And so for an initially acidic solution, the ratio is going to be 1/10, which means that our pH is equal to pKa minus 1. Well, if we know the pH, we can rearrange that equation to solve for the pKa is equal to 7 plus 1, which gives us a value for our pKa of 8. So from there, we can find an indicator with a pKa equal to 8 or a Ka equal to 1 times 10 to the negative 8. For strong acid, strong base titrations, indicator color changes are going to be very sharp, so it only takes the addition of just a single drop of titrant to get that color change. So you got to be really careful when you're doing a titration. Okay, and because it's so sharp, this also gives you several indicators that you can choose from, which is actually a good thing. For weak acid titrations, the weaker the acid being titrated, the smaller that vertical area on the pH graph or on the equivalence point. So if you take a look at this graph up here, this is what we're talking about with the vertical area. Strong acids are on the bottom, weak acids are on the top. So as you can see, as you get a weaker acid, your vertical part is much smaller. That means your range is much tinier. So you have less indicators to choose from. Okay, so less indicator choices. So the useful pH range needs to be as close as possible to the pH at the equivalence point. And so as you can see on our graph here, we've got two different indicators to choose from. Obviously, methyl red would not work because our equivalence point is up here. Thymol blue, however, would work because its range is covering the equivalence point. Okay, here are some problems to work on, and we'll discuss them more in class. Have a good day.